Common probability distributions. In this reading, we'll essentially talk about common probability distributions such as the discrete uniform distribution, binomial distribution, and then we will move on to continuous random variables where we will talk about the continuous uniform distribution, the normal distribution, which is perhaps the most important of all the distributions that we will study. We'll talk about the applications of the normal distribution, briefly cover the log normal distribution, and at a high level talk about the Monte Carlo simulation. A high-level introduction. Investment decisions require work with random variables. If you consider a very basic investment decision, which is whether or not to buy a stock, obviously we need to consider what the expected return on that stock will be. The expected return might be 12%, but this does not mean that the return will actually be 12%. It simply means that we are expecting 12%, and the actual return will vary around 12%. It might be more, it might be less, it might even be negative. So the return is a random variable, and it is important for us to understand how this random variable might be distributed or spread out, and that is what we will be studying in this reading. It is important to understand the probability distribution function of random variables. So that is what I'm talking about here. The distribution of that expected return is the probability distribution function. As I just mentioned, we will focus on four major probability distributions, which are shown right here. Perhaps the most important distribution is the normal distribution. Let us quickly review random variables, and first let's look at a discrete random variable. A discrete random variable is one where we can list all the possible outcomes. And we've talked about this briefly in the earlier reading, but stock price would be a discrete random variable because a stock price takes on specific values. The stock price at the end of the day might be $20, or it might be 20.01, 20.02, and so on. These are discrete values. Even though there is not a big difference between values, but there is still a discrete difference, and the values are also discrete. So stock price is a classic example of a discrete random variable. A continuous random variable is where the number of points between the lower and upper bounds are essentially infinite. And the classic example of a continuous random variable is the return on a given investment. If you buy a stock for 20.07 and then sell it for 20.19, the return that you make over here is going to be a very long decimal. So you can do the actual calculation and then you can calculate other returns. The return that you will report then will be rounded to 2 decimal places. So if you really think about it, the number of possible returns that you can have are infinite, because if you go down to hundreds of decimal places, then obviously the number of return numbers or the possible answers are infinite. When that happens, you have a continuous random variable, and as I said, the classic example would be the return on a stock. A probability distribution specifies the probabilities of all the possible outcomes for a random variable. If we are talking about a discrete random variable, then the distribution is essentially called a probability function. A probability function specifies the probability that a random variable takes on a specific value. If we are talking about a continuous random variable, then we use the probability density function. So a probability density function is used for continuous random variables. Let us now get into the discrete uniform distribution. This is our simplest distribution. So a classic example would be the rolling of a dice. The random variable is the specific outcome that you might get. So if you roll a dice, you might get 1 or 2 or 3 or 4 or 5 or 6. So these are 6 discrete outcomes. They are mutually exclusive and exhaustive. The probability of each outcome is 1 over 6, and that is why this is called a uniform distribution, because the probability of each outcome is the same. It is discrete because we have 6 discrete outcomes, and the cumulative distribution function, as we have studied in the previous reading, is simply the total probability up to that point. So the total probability that you get a 1 when you roll a dice is 1 over 6. The probability that you get 2 is 1/6, but the probability that you get 2 or less than 2 is 2 over 6. You are simply adding this. So the cumulative function or the cumulative probability is 2 over 6. This entire column is called the function, and a specific item over here is a particular cumulative probability. The cumulative probability for 3 would be the sum of these 3, which is 3 over 6. Now notice some terminology. The random variable in general is denoted by uppercase X. A specific value of the random variable, such as 2, is denoted by a small x. The probability of a certain variable, like we can say that probability of 2 can also be written as capital P, that the random variable x is equal to 2. So these are different ways of saying the same thing. In terms of the cumulative distribution function, we can write f of x. So f of 2 is equal to 2 over 6. This can also be written as the probability that the random variable is less than equal to 2. So that is also 2 over 6. You need to get used to this terminology, because in the questions that you work, either you might see notation like this or notation like this. Now let's evaluate a few expressions. What is the probability that the random variable is between 3 and 6, where 3 is less than equal to x, but x is less than 6? What that essentially is saying is that our random variable is between 3 and 5, because x is less than 6, so this 6 is not included in our discussion here, but 3 is, because of that less than equal to sign, which you need to watch very carefully. So the probability of 3 or 4 or 5 is essentially 1/3 plus 1/3 plus 1/3, which is 3 over 6. The cumulative probability f1 is simply 1 over 6. f4 would mean that we get to this point, so we add all these, that would be equal to 4 over 6. f6 is equal to 1, because that covers all 6 outcomes. And then f100 would mean what is the probability of the random variable taking on some value that is less than or equal to 100. And that probability is also 1, because all these 6 outcomes are covered under this situation. So they are all less than 100. The cumulative probability f0 would be 0, obviously. Now let's take a look at the binomial distribution. Before we understand the binomial distribution, we need to understand the building block of the binomial distribution, which is a Bernoulli trial. A Bernoulli trial is a very simple trial or experiment where you can have two possible outcomes, success and failure. Generally, success is denoted by 1 and failure is denoted by 0. There needs to be a certain probability of success, which is denoted by small p, which means the probability of failure is 1 minus p. A classic Bernoulli trial would be a coin flip. When you flip a coin, there are two possible outcomes. Either you will get heads or tails. Let's say heads means success. So the probability of heads would be 0.5 for a fair coin, and the probability of tails or failure would be 1 minus 0.5, which is 0.5. Another example of a Bernoulli random variable would be the stock price at the end of a period. So if you have a given stock price, you can say that either it will go up or it will go down. If the probability of going up is 0.6, then the probability of going down is 0.4, and therefore at times the stock price is modeled as a binomial random variable. Now, we've talked so far about the Bernoulli, which is a very simple scenario of two possible outcomes: success having a given probability and failure having 1 minus that probability. Let us now understand the binomial random variable. A simple way of looking at a binomial random variable is that it is a combination of Bernoullis, and when we combine the Bernoullis, let's say that we do 10 coin flips. Each coin flip is a Bernoulli. The question now is how many successes. Let's say heads means success. So how many successes will we have when we flip a coin 10 times? And if the question is asked, what is the probability that we will have 7 successes? The number of successes is the binomial random variable. So let us read what I have over here. A binomial random variable x is the number of successes in a given number of Bernoulli trials. In my simplistic example, we have done 10 coin flips, so n is equal to 10. That's the number of Bernoulli trials. And I am asking what is the probability of 7 successes. So x, which is the binomial random variable, is equal to 7. Similarly, we can ask the question, what is the probability of 3 successes? And this will be some other number. So the point is that x is the binomial random variable and x represents the number of successes with n Bernoulli trials. The next question is, what is the probability of x equal to 3 or x equal to 2 and so on? And to answer that question, we have to learn the probability distribution of a binomial random variable. Let us go through the material on this slide. The probability distribution of a binomial random variable for the probability of x successes in n trials is calculated using the following formula. If I were to continue with the simple example that I just talked about, and I ask the question, what is the probability that out of 10 coin flips I will have 7 successes, then what is the probability? The answer is given by this expression over here, ncx times the probability of a success to the power of x, 1 minus p, which is the probability of failure, into n minus x. In my example, n was 10 because we did 10 coin flips. So we'll say 10c7. 7 is the number of successes that we are considering over here, times the probability of success, which is 0.5, assuming we have a fair coin, raised to the power of x, that is the number of successes, and then 1 minus p, which is 0.5 to the power of 3. If you do the calculation, which ideally should be done on a calculator, so you should do 10c7 on a calculator and then multiply that by 0.5 to the power of 7 and then multiply by 0.5 to the power of 3, you should get 0.12. So this is the probability that if you flip a coin 10 times, you will get a success 7 times. Notice that the order of the successes doesn't matter. So you can get heads, which we are defining as success, the first 7 times or the last 7 times or somewhere in the middle, or you could have success, failure, success, success, failure, and so on. Now, you should memorize this formula, and then this formula can be used for 7 successes or 6 successes or even 0 successes. But let us also try and understand the logic behind this formula. Let us take the 7 successes example that we've talked about. To have 7 successes, one possible scenario is that your first 7 coin flips are successful and then the next 3 are not successful. So what is the probability of success 7 times and then failure 3 times? If you go back to your basic probability, the probability of success 7 times would be the probability of success times the probability of success 7 times. So we can just write that as 0.5 to the power of 7 multiplied by the probability of failure, which is 0.5, 1 minus the probability of success raised to the power of 0.3. So these two items are shown over here in the formula. The probability of success raised to the power of the binomial random variable, which is the number of successes, and then probability of failure times the probability of failure raised to the power of the number of failures. But then, since the order does not matter, we multiply this by the number of ways in which we can have 7 out of 10. So that is where the 10C7 comes from, because the number of ways in which you can get 7 heads out of 10 coin flips is depicted by 10C7. Now, whether or not you understood that explanation, you have to memorize this formula. Let's see if you can do the simple example now. What is the probability that a stock will move up on 7 out of the next 10 days, assuming that the probability of an up move is 0.6? Now remember, this can be modeled as a binomial random variable. We are talking about 10 days, so n is equal to 10. X is 7. The number of successes where the success is up move is 7, and we are asking the question, what is the probability that the stock will go up on 7 out of the next 10 days? But unlike the previous question now, the probability of success is 0.6, not 0.5. The way you solve this is by saying the following. So the probability that your random variable, the binomial random variable, is 7 is given by 10C7 multiplied by 0.6 to the power of 7, that's the binomial random variable, times the probability of failure times the number of failures. When you solve this, you should get 0.21. So this is the probability that the stock will be up 7 days in the next 10 days. And notice that this probability is a little higher than what we calculated on the previous slide, because the probability of success is higher. Next concept. What is the mean and variance of a binomial random variable? If you just take a simple Bernoulli, the Bernoulli is expressed as 1 comma p, 1 because with a Bernoulli you are just doing one coin flip or one experiment. There the mean value is the probability of p and the variance is p into 1 minus p. The real item we are after is a binomial. So for a binomial random variable, we depict it as bn comma p. When you flip a coin 10 times, then this will be written as b10 comma 0.5, because you have 10 coin flips and the probability of success is 0.5. So when we talk about the mean, the question is this: if you were to flip a coin 10 times, what is the expected number of successes? And just intuitively you can look at this and say that the expected number of successes is 5, because 10, which is the number of coin flips, times the probability of success with each coin flip is 0.5. The mean or the expected value is 10 into 0.5, which is 5. Now, every time you do this experiment, now the experiment is defined as 10 coin flips. Obviously, every time you do this experiment, i.e. flip a coin 10 times, you are not going to get 5 successes. Sometimes you might get 5, sometimes you might get 4, you might get 6, you might even get 0, you might even get 10 occasionally. So even though 5 is your expected value, the number of successes will be distributed around 5. Now, anytime you have a distribution, obviously that distribution will have a certain variance. The question now is, what is the variance for a binomial random variable? And the answer is this expression right here. The variance is given by n into p into 1 minus p. You don't need to understand where this formula comes from, you just need to memorize it. So in this simple example, the variance is equal to 10 into the probability 0.5 into the probability 0.5, because the probability of failure and probability of success are the same for a coin flip of a fair coin. Let us consider this simple example now. You have a 20 bond portfolio where each bond is from a different issuer. Each issuer has an estimated default rate of 10%. What is the expected number of defaults in the portfolio assuming a binomial model for defaults? This is fairly straightforward. N is equal to 20. The probability of a default is given by 0.1. We are asked what is the expected number of defaults. So the expected number of defaults would simply be the product of these two numbers, which is 2. Now this seems a little awkward, but here we are actually defining the default as a success just because of the way the question is worded. So the expected value is 2. What about the variance of the number of defaults over the coming year? As we've just seen, the formula for variance is n into p into 1 minus p. So the variance is equal to 20 into p, which is 0.1, into 1 minus p, which is 0.9, and this is equal to 1.8. To find the standard deviation, you simply take the square root of the variance. Let us do this practice problem now. You are estimating the earnings of a company over the next 10 years. Based on past data, the probability that earnings will increase in a given year relative to the prior year is 0.8, which means that the probability of this not happening, or the probability of failure, is 0.2. What is the probability that the earnings will increase in exactly 5 of the next 10 years? Here you use the first formula that you learnt in this segment, which is that probability of 5 successes, so probability of x is equal to 5, is equal to 10c5 in this particular scenario next 10 years. So n is equal to 10. The binomial random variable is equal to 7. The probability of success is equal to 0.8. So let's regurgitate the formula here. 10c5 into probability of success raised to the power of number of successes, probability of failure raised to the power of number of failures, which is n minus x. And then plugging in, so 10c5 we can calculate. Let me just write 10c5 again, multiplied by p, which is 0.8 to the power of x. X is 5, and then 1 minus p, that's the probability of failure, 0.2 raised to the power of 5 again. When you solve this, you should get 0.026. So this is the probability of exactly 5 successes in the next 10 years. Next question, what is the expected number of yearly earnings increases? Here we simply use the formula n times p, which is 10 multiplied by 0.8, which is 8. So we expect 8 successes over the next 10 years because of this probability. And finally, what is the standard deviation? And notice the question is asking for standard deviation. We will find the variance and then take the square root. So the variance is given by n into p into 1 minus p, which is equal to 10 into 0.8 into 0.2, which is 1.6, and then you take the square root of this for the standard deviation. We now move to the world of continuous random variables, and we will talk about the continuous uniform distribution, the normal distribution, applications of the normal distribution, and finally the log normal distribution. Let us consider the continuous uniform distribution first. The continuous uniform distribution is defined over a range that spans between some lower limit a and some upper limit b. Let us say that we have a random variable which is uniformly distributed between 5 and 10. The continuous uniform distribution will simply look like a straight line. It is uniform, that is why we have a straight line. What that means is that the random variable will be between 5 and 6. So the probability is denoted by this area over here. That probability will be the same as the probability of the random variable falling between 6 and 7, and so on. The overall probability that the random variable falls between 5 and 10 is equal to 1. That means that the total area of this rectangle is 1. So the probability that the random variable falls between 5 and 6 is equal to this rectangle, the smaller rectangle over here, or essentially the bar. That probability is simply 1 over 5. The probability of the random variable between 6 and 7 is 1 over 5, and so on. If you add all these 5 numbers, so 5 to 6, 6 to 7, 7 to 8, 8 to 9, and 9 to 10, you should get the total probability of 1. The next question is, what is the height of this rectangle? We have already established that if the rectangle base is going from 5 to 10, so the width is 5. We've established that the area is 1. So remember from your basic mathematics that area is base into height. If the area is 1 and the base is 5, then the height must be 1 over 5. That 5 is essentially b minus a, which in our example is 10 minus 5. So this is fairly straightforward. If I ask you what is the probability that the random variable is less than 7, then essentially I am asking what is the probability of this rectangle, because anything less than 5 has a probability of 0. The probability that the random variable is less than 7 is simply 2 divided by 5. So that is also the area of this rectangle. So this is fairly straightforward once you understand what is going on. Let us look at an example. Random variable x follows a continuous uniform distribution between 10 and 20. What is the probability of an outcome between 15 and 25? So all you do here is recognize the fact that our random variable is between 10 and 20, and we want to know what is the probability of being between 15 and 25. If we are to draw this out, we need to recognize that the base is equal to 10. So 20 minus 10 is 10. We know that the area, total area, is going to be 1. So what is the height? The height is simply 1 over 10, because 1 over 10 times 10 is going to be 1. The question now is, what is the probability that the random variable is greater than 15? So that essentially is this shaded rectangle. There is nothing over here because this probability is 0. So the probability of being between 15 and 25 is the same as the probability of being between 5 and 20. Now you can simply see that this is half of the total area. So the probability is 5 over 10, which is 0.5. Again, I'll just emphasize that this is fairly straightforward. And one other point that you should recognize is that when we have a continuous uniform distribution, we always speak in terms of a range. So the probability of an outcome between 15 and 20 or between 15 and 15.5. So there is always a range. The reason is that the probability of a specific number, so probability of 15 is going to be essentially 0. And given that there are an infinite number of possibilities between 10 and 20, the probability of one specific number is effectively 0. So that's why there is always a range that we talk about in the context of continuous distributions or continuous random variables. We are still on the continuous uniform distribution, but now we will look at a cumulative distribution. If you recall from our earlier discussion, when we say cumulative, we are essentially saying that the probability of a random variable being less than or equal to a certain number. If we continue with the example we just talked about, we are going from 10 to 20. So the cumulative distribution would essentially be px less than or equal to a specific value of the random variable. If I say px less than or equal to 15, that is the cumulative probability up to 15. So that means all the probability that we accumulate up to this point in time. So that cumulative probability is equal to 1 over 2, and we just saw that. The way you can see this is the cumulative probability up to this point in time is 0. So if you bring this down over here, at the bottom we have the cumulative probability. So up to point 10, so random variable is equal to 5, the cumulative probability is 0. Even at 10, the cumulative probability is 0. But as we start increasing beyond that, then the cumulative probability starts rising because we are accumulating all this probability. When we are at 15, which is the midpoint, then the cumulative probability will be 0.5. As you get to 20, the cumulative probability becomes 1. After that, as you keep increasing, the cumulative probability stays at 1 because here the probability is 0, so you are not accumulating any more probability. Cumulative probability is also expressed using the letter f. So f of 15 in our example is the probability that the random variable is less than or equal to 15, so that is 1 over 2. F of 20 is equal to 1. F of 100, so anything more than 20, would also be equal to 1. Let's look at this practice question now. The execution time for a single order is uniformly distributed between 10 and 18 minutes. If an order is placed at 2:30 p.m., what is the probability that the order will execute after 2:45? So here is how you can do this. Let us say that we are currently at time 0. So the order is placed at 2:30. Now the order will take place between 10 and 18 minutes, and we have a uniform distribution. So that means that the order will execute somewhere between 2:40 and 2:48. The question is, what is the probability that the order will execute after 2:45? So if you simply look at this, we are asking for this probability. That is simply equal to 3. This is 3 in the numerator divided by the total distance, which is 8. So the probability is 3 over 8.